In this lecture, we mostly discuss the problems of integration as a limit of a sum, or what we call as the Riemann sum. We have seen some of the questions based on Riemann sum in the last class. Okay. We briefly recall what is exactly this Riemann sum means, and then we'll continue with a lot of questions actually. We have the sum. If we have any of this format, limit n tends to infinity, we know that limit n tends to infinity 1 by n, summation r is equals to 0 to n minus 1 f of r by n. If we have any of this format, then we solve this by integrating from 0 to 1 fx dx. What is the concept actually? We replace this r by n by x over here. Wherever we have r by n, function of r by n, we try to locate the if we have the function of r by n, and then we figure out what function is there, and in the place of r by n, we simply replace by x. Okay. Then this summation is now replaced by this integration. Limits of this integration is dependent on the limits of the summation. We have also discussed how to determine the limits also. We will recall the same again also. And over here we have dx. Now 1 by n is actually replaced by dx. This is the main thing. So any integration of this format, we have also proved this, if you remember. We have also proved this in the last class. So any integral of this particular format, any limits, summation series of this particular format is solved by integration, definite integration rather. Once again, I'll repeat that the limits of this integration is completely dependent on the summation, limits of the summation. Let's look at some questions. Okay, here we have the first question. Evaluate this limit given by limit n tends to infinity 1 by n plus 1 plus 1 by n plus 2 up to 1 by 2n. How do we solve this limit? What we do first, we have to first bring this into the format of limit n tends to infinity and sigma. We have to write this in terms of sigma representation, and then we have to find out what is the r by n function over here. So what I do, here we have limit n tends to infinity. So this is limit n tends to infinity. In terms of sigma, I want to write it. So this is summation r is equals to 1 to n. Obviously, we have 1 by n plus 1, 1 by n plus 2, and so on. This 1 by 2n is what? This 1 by 2n is basically 1 by n plus n. So here I can write this as the summation goes from r is equals to 1 to n. Okay, and this is basically the function of n 1 upon n plus r. Obviously, you put r is equals to 1, so here we have 1 upon n plus 1. You put r is equals to 2, so you will have 1 upon n plus 2, and so on. You put r is equals to n, you will have 1 upon n plus n. So that's 1 upon 2n basically. Okay. So now I try to bring this into the format of limit n tends to infinity 1 by n summation r is equals to 1 to n. F of r by n, function of r by n. Here we cannot see any function of r by n. So we need to simplify this a bit. What I do, I take out n common from the denominator. So I get this to be limit n tends to infinity. I take out n common from the denominator. You can take out outside the summation also, because we have 1 by n. N is, the summation is actually independent of n over here, right? The summation is dependent on r. So this is r is equals to 1 to n. And this goes from 1 upon 1 plus, because we have taken out n common from this, is 1 plus r by n. So now we can locate this function of r by n over here. This is the function of r by n. Okay. So now what we do, limits goes from r is equals to 1 to n. So here we replace this. So this entire thing will now convert to integration 0 to 1. Obviously, limit goes from 1 to n. So integration will also goes from 0 to 1, 1 upon 1 plus x dx. Okay. Idea is very simple. for the limits, for changing, like how to determine the limits, it depends upon the, I told you, it is dependent on the limits of the summation. Okay, the upper limit and the lower limit of this integral is completely dependent on the limits of the summation. Idea is very simple. If you try to understand over here, we have the lower limit, integration a to b. We are saying this is integration a to b fx dx. This is the lower limit and this is the upper limit. For the lower limit part, I'm saying, for the lower limit, what you do over here itself, in the lower limit, what is the lower limit of the sigma? R is equals to 1. So what do? You divide by n and take limit n tends to infinity. Okay, to determine the lower limit of this integration, what we do is we divide by n over here and then we take limit n tends to infinity. So if you divide by, we have the lower limit of this sigma to be what? R is equals to 1. Okay, so you take this, divide by n and then take limit n tends to infinity. So this tends to 0. Okay, so we have the lower limit to be 0. And for the upper limit, I'm saying, what is the upper limit of sigma? Upper limit of sigma is n. So you do the same thing, divide by n and take limit n tends to infinity. Okay, divide by n and take limit n tends to infinity. So we have n, so n by n. Okay, so this is how much? 1 only. So that's why we're having 0 to 1. Otherwise, there is one more way to determine these limits. If you want to see this, over here we have integration that is going from 0 to 1. Actually, what I can do over here is we have r by n function over here. So first of all, we have the limits of the sigma. Actually, the limits of this summation goes from 1 to n, right? So basically, r is going from 1 to n. We want the limits of r by n, so we divide by n over here. So this becomes r by n less than 1. Okay. Now over here we take limit n tends to infinity. If you take limit n tends to infinity, this will tend to 0. So we have 0 less than r by n less than 1. R by n is now replaced by x. So we have 0 less than x less than 1. So this is your limits of this x actually. These are your limits of x. So we have limits of x to be 0 to 1. This way also you can find, or this way also you can find. So this is simply given by integration 0 to 1, 1 upon 1 plus x dx. Now we solve this integration. Simple solving this integration. So this is ln 1 plus x. Okay, range goes from 0 to 1. So this converts to ln 1 plus 1, which is 2. Okay, minus ln 1, log 1 is 0. So we have ln 2 over here. Answer is ln 2. Okay. Otherwise, simple, you can just learn one short trick also. We have a short trick for this particular question also. This question could have been given in this manner, limit n tends to infinity. We have 1 upon n plus 1 plus 1 upon n plus 2 and so on up to let's say 1 upon 3n. This could have been up to 1 upon 3n. This could have been up to 1 upon 4n. This part I'm saying. Okay. Likewise, you have to evaluate. This could have been up to 1 upon 2n. Like in the place of 1 upon 2n, we would have simply got it to be 1 upon 3n. Okay, 1 upon 3n, 1 upon 4n. In that case, for 1 upon 4n, suppose if this would have been, the summation goes up to 1 by n plus 1 plus 1 by n plus 2 and so on up to 1 upon 4n. So for 1 upon 4n, what we do? We'll write this as 1 upon n plus 3n, isn't it? We'll write this as 1 upon n plus 3n. Accordingly, we'll have the limits of this sigma from r is equals to 1 to 3n, isn't it? For example, I'm saying this thing that basically if the sigma goes from in this manner, we have the limit given to be limit n tends to infinity 1 by n plus 1 and so on 1 by n plus 2. We have up to n plus 3n, like means 3n is 4n is there, so that's basically 4n, which means I write this as n plus 3n. So in this case, sigma would have been gone from sigma limit n tends to infinity. Sigma, the limits of the sigma will be from r is equals to 1 to 3n. Okay, 1 by n plus r. So in this case, limit n tends to infinity. We'll try to represent in this format, but only change will be integration would have been gone from 0 to 3. Very basic idea, because your R is now from where to where? R is now from 1 to 3n. So for the lower limit, you divide by n and take limit n tends to infinity. So this will be the same thing, 0 only. But for the upper limit, we have 3n over here. You are dividing n and then taking limit n tends to infinity. So obviously, this will become 3 only, isn't it? So integration would have been gone from 0 to 3, not 0 to 1. This was from 0 to 1, so this will simply go from 0 to 3 fx dx, 1 by x dx. So for such type of problems, we could have been given from 1 by n plus 1 and so on up to this could have been given up to 1 by 4n, 1 by 5n and so on. So for this case, you can remember one short trick for this particular type of questions. This 1 by 2n actually will determine your answer. This 1 by 2n actually determines your answer. If this is 1 by 2n, then the answer will be log 2. If this is 1 by 3n, answer will be log 3. If this is 1 by 4n, then the answer will be log 4. Okay. So you can write it in your own language that this is one short trick which I am giving over here, that this 1 by 2n determines actually what is the answer of this particular series when limit n tends to infinity. Okay. Okay, now we have this question. Evaluate this limit given by this 1 by n plus n square by n plus 1 whole cube. I told you, and any of this format will be given, and first of all, you have to represent this in terms of sigma. Okay, simplify. Maybe you have to simplify in some cases, or maybe you do not have to simplify, directly it is visible. Here the first term is 1 by n. How they have adjusted? Second term is n square by n plus 1 whole cube. Third term is n square upon n plus 2 whole cube, and so on up to 1 by 18. Idea is very simple. I rewrite this limit, this sum actually. Limit n tends to infinity. Just to represent this in terms of sigma, we need this to rewrite this actually. So we have 1 by n over here. This 1 by n has been adjusted over here. You see the numerators of each term is basically n square. So this is n square upon n plus 0 whole cube. You can verify n plus 0 whole cube, we have n cube only. Numerator we have n square. So this is 1 by n. Then we have the second term to be n square upon n plus 1 whole cube. Third term is n square upon n plus 2 whole cube. And so on. Now the last term, we have 1 by 8n actually. Okay. The numerator will be n square. Now 8n means what? That is basically simply n plus n whole cube. N plus n whole cube. Isn't it? Now we can represent this in terms of sigma actually. So this is actually limit n tends to infinity. Sigma. R starts from 0 to 0, goes up to n. Here we have n square, so we write this to be n square. And denominator we have n plus r the whole cube. Okay. N plus r the whole cube, you can verify also, you put r is equals to 0, so we have n square upon n plus 0 whole cube. You put r is equals to 1, this is basically n square upon n plus 1 whole cube. You put r is equals to n, so we'll get n square upon n plus n whole cube. Okay. So now our target is to bring this r by n format over here. What I do over here, we have to bring r by n over here. Numerator we have n square, denominator we have n plus r whole cube over here. So one thing I can clearly see, if I divide by n cube over here. Okay, if I divide the numerator and the denominator by n cube, so what I get from here, we have limit n tends to infinity, 1 by n comes out, so this is summation r is equals to 0 to n. Okay, we are dividing by n cube over here, so n square is there now, so we are dividing by n cube, so n cube means 1 by n will be remaining, so 1 by n comes out. Okay, and this is 1 upon You're dividing by n cube, both in the numerator and denominator. So this turns out to be 1 plus r by n, the whole cube. Okay. Fine. So now what we do? Now this is our standard formula. This is a function of r by n. Okay, this is a function of r by n. Now what we do? We replace this by integration 0 to 1, because integration limits of this sigma goes from 0 to n. So this is integration 0 to 1 dx upon, okay, dx upon, the function is what? 1 upon 1 plus, replace r by n by x. So we have 1 plus x the whole cube. This is a function. Our function fx is basically 1 upon 1 plus x. Clear? That's what we are having. So now this is easy integration. Basic integration. This is how much? This is 1 plus x whole to the power minus 3. So that is basically minus 1 upon 2 times 1 plus x the whole square. Range of this integration goes from x is equals to 0 to 1. So you put this over here. So this is, if you put this over here, so we get 1. For 1, what we get from here? We have minus 1 by 2 times 1 plus 1. So we have 2 square 4, right? So we have minus 1 upon 2 times 2 squared. So this will become 4. Okay. And over here minus minus. So minus was already there. Minus 1 upon 2. Okay. I have this to be minus of 1 by 8 minus half over here. So if you simplify this, so that's half minus 1 by 8. Okay, which is 3 by 8. Let's see some more questions of this type. Okay, this is a very simple problem asked in ISI BStat BMath 2020. You have to find the limit of this sigma k is equals to 1 to n e to the power minus k by n upon n as n tends to infinity. A similar question was also asked in JEE also. So we have they have asked this thing to find out that what is limit n tends to infinity e to the power minus kn k by n upon n. We have sigma k is equals to 1 to n. You're asked to find out this limit actually. Very simple. This is already of the form limit n tends to infinity. You can take out this 1 by n outside of this sigma. Sigma is dependent on k. K is equals to 1 to n e to the power minus k by n. Very simple. So what we have, this is as basically, this is integration 0 to 1 e to the power minus x dx. Fine. So this is how much? So this is integration of e to the power minus x. So this is minus e to the power minus x. Range goes from 0 to 1. So this is minus of e to the power minus 1 minus e to the power 0. This is 1. So we have 1 minus 1 upon e. Okay. So option C is correct. Very simple problem asked in ISI BStat BMath 2020. So there's a very scoring portion if any question is asked from this particular part. As I said, maybe they can give it in this format. Already it is in terms of sigma, or it may happen that they will give it in terms of series and we have to bring it into the form of sigma by simplifying it. And normally you will find the second one only, like the series will be given and this has to be expanded. This has to be simplified and we have to bring into the format of f of r by n. R by n format we have to bring and then we have to integrate. Okay, so they'll give it in such a manner that you have to simplify. Okay, next we have this question. We have to evaluate this limit n tends to infinity 1 by n square sec square 1 by n square and so on up to 1 by n sec square 1. This is a JEE problem actually. What I have, the first term is 1 by n square sec square 1 by n square. Second term is 2 by n square sec square 4 by n square. Okay. Then the last term is 1 by n sec square 1 So what we can say about this term? Sec square 1 is given. Here this is actually, if you see the format, 1 by n square, 2 by n square. So definitely 1 by n means n by n square. Okay, 1 by n is nothing but n by n square. We can write this as n by n square. And we have sec square 1 by n square, sec square 4 by n square. And here we have sec square 1 is given. So basically, what is this last term actually? This sec square 1 is basically sec square n square by n square, because this 1 by n square is nothing but 1 square by n square. This is 2 square by n square. So obviously the last term will be n square by n square. So that is why they are getting 1 over here. So this is sec square n square by n square. We can now solve this and bring this into the format of sigma. This is limit n tends to infinity, summation r is equals to, r starts from where to where? R starts from 1 to n. Okay, we have 1 by n square, 2 by n square. So we can write this to be r by n square. And this is sec square r square by n square. Okay, you put r is equals to 1. So we have 1 by n square. First term will be 1 by n square, sec square 1 by n square. You put r is equals to 2. So this will be 2 by n square, sec square 2 square by n square. That's 4 by n square. Second term will get. Similarly, at the end, if you put r is equals to n, so we get n square by n square, that is 1 by n. Okay, n by n square, that is 1 by n, and sec square r square by n square. So you're putting r is equals to n, so this will become n square by n square, that is 1. So this is getting balanced over here. So this is basically, how much is this now? What do we do? We try to express this in the form of 1 by n sigma f of r by n. So this is limit n tends to infinity. One of the 1 by n can be given from here. So this is 1 by n sigma r is equals to 1 to n. R by n must be there, and sec square r by n must be there. So this is obviously of the form f of r by n. This is a function of r by n. Outside also we have 1 by n. So clearly we can write this as integration 0 to 1. Limits are from 1 to n, so integration will go from 0 to 1. Okay, and replace r by n by x. So we have x. Here this is r by n whole square. So this is how much? So this is basically x square x sec square x square dx. Okay. Now we take the substitution x square is equals to t. So if you take the substitution x square as t, so this will become 2x dx to be dt, or x dx is dt upon 2. Okay. So half comes over here. You can also change the range of this. You put x is equals to 0 over here. T will be 0. You put x is 1. T will be still 1. So integration will be the same. Range will be the same. And that is basically integration 0 to 1. X dx is dt by 2. So half comes out. So we have dt over here, and sec square x square. So we have sec square t over here. Okay. So this is basically half integration of sec square t. That is basically tan t. Range goes from 0 to 1. So this is half times tan of 1 minus tan 0. Okay. So that is basically half times tan 1. So you can see how simple problems are if you can easily try to represent this in terms of sigma. Once you represent this in terms of sigma, problem becomes very easy. Let's see the next question. Okay, we have been asked to evaluate this limit, which is given by limit n tends to infinity, 1 plus 1 by n, 1 plus 2 by n, up to 1 plus 4n by n whole to the power 1 by n. How do we solve this? Obviously, first we have to think of to try to bring this into the format of sigma r by n. But the problem here is, here we don't have sum. Instead, we have product in this case. Product of terms are given 1 plus 1 by n into 1 plus 2 by n and so on up to 1 plus 4n by n. And in the power we have 1 upon n. So what I do in this case? In this case, we will take log on both sides and then simplify, because one idea we can have here, we have numerator, in the numerator we have in the power we have 1 by n. So if you take log, 1 by n comes down. Also we have log a into b into c up to n times we have, so that is basically log a plus log b plus log c. So some format we can generate from there, right? Okay, log ab is basically log a plus log b. From there only this idea of this summation series will come to your mind. So here what I do is I consider this limit to be a over here. I take log on both sides. You know, log of limit and limit of log are the same thing, so you can take this log. So log of a is equals to limit n tends to infinity, and this is basically you're taking log over here. So this is log of 1 plus 1 by n, then 1 plus 2 by n, and so on up to 1 plus 4n by n, whole to the power 1 by n. So how much is this? So this is basically limit n tends to infinity, log of. Now what do? We have log of this thing and power is 1 by n. So 1 by n can come down over here, right? 1 by n comes down. And we have log of 1 plus 1 by n. Let me write this 1 plus 1 by n. We are left with this 1 plus 2 by n up to 1 plus 4n by n. How do we simplify this now? We can represent this in terms of sigma, but initially we simply use the properties of log actually to break this. This is in terms of product. So how much is this? Log a, log a1 into a2 and so on up to an. This is basically log a1 plus log a2 plus log a3 up to so on up to log a. Properties of logarithm we are using. So this is actually limit n tends to infinity 1 by n. We have log a1, we have log of 1 plus 1 by n plus log of 1 plus 2 by n and so on up to log of 1 plus 4n by n. Now we can represent this in terms of sigma. So this is basically limit n tends to infinity 1 by n. Sigma r is equals to, sigma goes from where to where? We have r is equals to 1 to, this is going up to 1, 2, 3 up to 4n. So sigma goes from r is equals to 1 to 4n. And this is log of 1 plus r by n. You can verify this is already balanced. You put r is equals to 1. So this is log of 1 plus 1 by n. You put r is equals to 2. So this is log of 1 plus 2 by n. And lastly, you put r is equals to 4n. So this is log of 1 plus 4n by n. Okay. Now sigma goes from where to where? Sigma goes from 1 to 4n. So obviously in this case, limits of the integration would be going from 0 to 4. Okay. This is a function of r by n. So this is now converted to integration 0 to 4 log of 1 plus x dx. Okay. So now this is easy integration. How do we integrate this? We integrate by parts. Okay. Integration by parts of this particular definite integral. So let us by parts integrate this by parts. So what I have from here, we have this is actually log a. Never ever forget this thing. So one mistake I have seen students often do make is taking this log a over here and they do not replace this log a at the end. Okay, this is one common mistake, a very silly mistake, although you are solving for log a, you're not solving for a over here. You have to replace this a also, right? You have to write it in terms of a, not log a. So after solving this, you have to replace by this, you have to convert this log, actually this is log a is given, so you have to solve for a actually. So what I do over here, we have log of 1 plus x. I integrate this by parts. So we have the first function. What is the first function? We have log of 1 plus x into 1. So we have the first function to be, this is our first function and this is our second function. Second function means 1 over here. This is our second function. So what I do, I integrate this by parts. So here we have the first function is log of 1 plus x. First function, integration of second function, that is basically x. Okay, range goes from 0 to 4 minus integration 0 to 4. We have the differentiation of the log of 1 plus x, that is basically 1 upon 1 plus x. And then we have integration of x, integration of dx, that is basically x. Okay. Now it is easy to simplify. We have log of 1 plus x into x. You simply put this limit, integration going from 0 to 4, x upon 1 plus x. To solve this, what we do? We add 1 and subtract 1. Very simple integrations and simple calculations over here. So how much is this? Basically, you put x is equals to 4 over here. So we have 4 into 4 plus 1. That's 5. So we have log 5. 4 times log 5 minus, integrate this thing. We have integration 0 to 4. We need to simplify this a bit. We have integration 0 to 4. Okay, this is plus 1 minus 1. So dx minus minus plus. So we have 1 by 1 plus x. So this is basically, you can directly write this to be x upon, this is directly x minus log of 1 plus x. Range goes from 0 to 4. So this is 4 log 5 minus, this is actually, you put 4 over here. So this is 4 minus log 5. For 0, this will become 0 because log 1 plus 0, that's log 1. Log 1 is 0. Okay. So how much is this now? So 4 log 5 and plus log 5, that is basically 5 log 5. So 5 log 5 minus, over here we get 4 over here. Now 4 you can further simplify, like in the answer, if this would have been given in the objective type question, they will simplify the options. Okay. Likewise, you also can simplify, like over here we have log 5. So they'll give it from maybe they can give it from log 5 to the power 5. Okay. And maybe they can change this 4. We need to change this 4 from log. We can make this to be log e to the power 4. So this turns out to be log 5 to the power 5 upon e to the power 4. This way also we can simplify. Okay. So various types of simplifications depending upon the options you might have to do. Now this is actually log a. Log a is this thing. Okay. Now you have to, log a is this thing. You have to simplify this, isn't it? Log a is this thing, which means a will be what? 5 to the power 5 by e to the power 4. Isn't it? Log a is this thing. So which means a will be 5 to the power 5 by e to the power 4. This is your final answer. Okay, here we have this question asked in JEE Mains 2016. You're asked to evaluate this limit n tends to infinity. Again, some product terms are given. 4 to the power 1 by n is given. Simple idea. What I do? Over here, I take this to be a, suppose. I evaluate this by taking log on both sides, right? Over here, one thing you can understand. Here we have n plus 1, n plus 2, n plus 3. And denominator, we have n to the power 2n. In fact, you can simplify this over here. We have limit n tends to infinity. You can distribute this n to the power 2n actually. N to the power 2n means n into n into n into n up to 2n times actually, right? Because over here we have 3n and this 3n is nothing but n plus 2n actually. Okay. So this is actually n plus 1, n plus 2 and so on up to n plus 2n. And denominator we have n into n into n up to 2n times, because in the numerator how many terms are there? 2n terms are there. So basically in the denominator we have n into n into n up to 2n times. So that's why we are having n to the power 2n. So these n's actually we can equally distribute with the numerator terms. Like over here we have n, n and so on. We can equally distribute these n to the power 2n. And power we have 1 by n over here. Now I take log on both sides and simplify this. If you take log on both sides, so this is log a is equals to limit n tends to infinity over here. So this is 1 by n will come down over here. If you take log over here, 1 by n comes down. And this is log of, this is 1 plus 1 upon n. You can divide this n over here. So this is 1 plus 2 by n and so on up to 1 plus, this goes up to 1 plus 2 by n. Okay. So now what I have? So this is basically limit n tends to infinity. Now I use the properties of log. So this is log a, b and c and so on. Okay, like log a1 into a2 into a3 and so on up to an is basically log a1 plus log a2 plus log a3 and so on up to log a. So this is actually basically log 1 plus 1 by n plus log 1 plus 2 by n and so on up to log of 1 plus 2n by n. We bring into these terms just to bring into the summation format. So this is summation what? We have limit n tends to infinity 1 by n. This is sigma f of r by n. We have log of 1 plus r by n. You see from here 1, 2, 3 and so on. The terms are going like this: 1 plus 1 by n, 1 plus 2 by n. So obviously we have 1 plus r by n, where r is going from 1 to 2n actually, right? You put r is equals to 1, so this will become 1 plus 1 by n. You put r is equals to 2, so this will become 1 plus 2 by n. You put r is equals to 2n, this will become 1 plus 2n by n. So that's why we are getting sigma going from r is equals to 1 to 2n. Now this is simple integration 0 to 1. So this is simple. So this will be integration 0 to 2 because limits are going from r is equals to 2n. R is equals to 1 to 2n. So obviously integration limits will be going from 0 to 2 and the function of r by n. So this is basically r by n is replaced by x. So we have log of 1 plus x dx. Now again, same thing, only integration is going from 0 to 2, log of 1 plus x dx. Just now we have integrated log of 1 plus x dx. Okay, this integration I am leaving out for you. You will solve this integration, put those limits and you will get the answer. Okay, this much integration you all can solve. Take integration, simply integrate this by parts. Just now we have solved integration log of 1 plus x dx by integration by parts. Integrate that, put those limits and you will get the answer. Very simple idea. So if you just now, I just say that obviously like you get the you get to represent this. If you know the representation, we can easily represent this. You can identify function of r by n, sigma, limits of sigma, then easily you can solve the question. Okay, next we have this question. We have to evaluate this limit n tends to infinity n factorial whole to the power 1 by n upon n. We have two methods to solve this particular limit. One is this Riemann sum. Another method is actually a very standard method. We call that Cauchy's theorem and limit. Let's first solve this by the Riemann sum method and then we'll see the second method. We have limit n tends to infinity n factorial whole to the power 1 by n upon n. How do we solve this? We can write this n factorial. We have limit n tends to infinity. We have n factorial. N factorial means n into n minus 1 up to 3 into 2 into 1. So basically I can write this numerator as 1 into 2 into 3 up to n. Okay, by n, and over here we have whole to the power 1 by n with the numerator. In fact, this whole to the power 1 by n can be taken for the entire limit. What I'm trying to say, you can take the whole power 1 by n in the place of only numerator. We can take this with the whole power 1 by n, but in the denominator we don't have any power 1 by n over here. So obviously to balance this thing, I will simply take power n over here. I'll simply take power n over here, isn't it? Okay. Over here, if you just take 1 by n power in the denominator, so this will become n to the power n by n, which is n only. Fine. So now I can distribute these n to the power n. Now here in the numerator we are having n terms, 1 into 2 into 3 up to n terms, and denominator we are also having n terms, like n into n into n into n up to n times. Okay, so we can distribute with each of these terms actually. So this turns out to be limit n tends to infinity. This is 1 by n. We can distribute with each of these terms actually. So 1 by n into 2 by n into 3 by n and so on up to n by n whole to the power 1 by n. We consider this to be some limit is a, suppose, and then we take log on both sides. Similar type of problem. So we take log on both sides and then we simplify. You take log a over here on the left hand side. So this will become limit n tends to infinity. Okay. So this is You take log over here, so 1 by n comes down. So the 1 by n log of 1 by n into 2 by n and so on up to n by n. Now use the properties of log over here. So this is limit n tends to infinity 1 by n log of this thing. So we have log a plus log b. This will turn out to be log 1 by n plus log 2 by n and so on up to log n by n. So clearly we can write this in terms of sigma now. So limit n tends to infinity 1 by n. Sigma r is equals to 1 to n. Okay. We are taking sigma from r is equals to 1 to n because over here we have 1 by n, 2 by n, so on up to n by n. There are total n terms going up to from 1 to n. So we are taking sigma from r is equals to 1 to n, and this function of r by n will be log of r by n. You put r is equals to 1, so this will become log of 1 plus log of 1 by n. You put r is equals to 2, this will become log of 2 by n and so on. This will become log of n by n. Okay, easy. So next what we simply replace the sigma by integration. So this is integration. Limits will be from where to where? Limits will be from 0 to 1. Integration is going from 1 to n. So limits will be from 0 to 1. F of x dx. Right? 1 by n is now dx. And r by n is now replaced by x. So this is the function of r by n. So this is f of x. So this will become log of x dx. Okay. Now this is a very common integration, log x dx. All of you know this thing. Log x dx. How do we integrate log x dx? Integration by parts. By this time you should be knowing these type of all basic integrals. So integration of log x dx is x ln x minus x. It is x log x minus x. Range goes from 0 to 1. Simple integration by parts. Okay, taking log x as the first function and then 1 as the second function. Simple integration by parts. Take this as the first function and this is the second function. Okay, and then we integrate by parts. So this is just x ln x minus x. So this is basically you put the limits over here. So you put 1 over here. Log 1 is 0 minus 1, and for 0 this will become 0. So this is minus 1. Now log a is minus 1. See, log a is minus 1. Okay, log a is minus 1. So definitely a is basically e to the power minus 1. This thing you have to be very careful of. Okay. What happens is in a hurry, a lot of students create this mistake that taking log a over here and they forgot to replace this a by e to the power minus 1. Okay. Like over here, we don't have any minus 1 in the options. If there would have been one minus 1, would have gone wrong in this case. Right? It's a very silly mistake kind of thing, a very common type of mistake. Okay. Okay, I hope this Riemann method is clear. This Riemann sum method is clear. We see one more way to solve this particular question, which is known as Cauchy's second theorem on limits. Let's see what is Cauchy's second theorem of limits. So I've given the Cauchy's second theorem of limits over here. This is actually true for all sequences. Here we have taken A to be one sequence. The Cauchy's second theorem of limits is a very advanced part of sequence. It comes under the limit of a sequence. Okay. But initially, wherever it is applicable for all limit questions, you can apply this Cauchy's second theorem on limits. It says limit n tends to infinity, an plus 1 by an is equals to the same as the limit n tends to infinity, an whole to the power 1 by n. These two limits are same. This is known as Cauchy's. Like this is only small statement, which is known as the Cauchy's second theorem on limits. Okay. In this case, we try to apply the same over here. We have limit n tends to infinity. Question was limit n tends to infinity, n factorial upon n whole to the power 1 by n. We simplified this and we wrote it as limit n tends to infinity, n factorial upon n, entire thing whole to the power 1 by n. So try to figure out this thing. Over here you can see that we are getting something of this format. Here an is what? An is n factorial upon n. And we have limit n tends to infinity whole to the power an whole to the power 1 by n. Clear? So we try to take the help of this Cauchy's second theorem on limits. We try to evaluate this limit n tends to infinity, an plus 1 by an. we try to evaluate this particular limit. So by Cauchy's theorem, we can simply generalize this thing. So we try to figure out what is limit n tends to infinity an plus 1 by an. Clear? So what is an in this case? An is basically an plus an is n factorial upon n to the power n. Okay. And an plus 1, what is an plus 1? An plus 1 will be n plus 1 factorial whole to the power n plus 1 whole to the power n plus 1. At the place of an, if an is this thing, so obviously an plus 1 in the place of n, we'll simply replace by n plus 1. This is n plus 1. Clear? So we now try to find out this limit actually, limit n tends to infinity an plus 1 by an. We try to simplify from there itself. So this is limit n tends to infinity an plus 1 upon an is actually limit n tends to infinity. That is n plus 1 factorial upon n plus 1 whole to the power n plus 1 upon an. So upon an means we can simplify this and write it as n to the power n upon n factorial. Clear? Now we try to simplify this particular limit. Let's solve this limit. So we have limit n tends to infinity. This n plus 1 factorial, we can write it as n plus 1 into n factorial. Clear? And this n plus 1 whole to the power n plus 1, we can write it as n plus 1 whole to the power n into n plus 1. And here we have n to the power n, and this is n factorial. So clearly we can see that n factorial cancel out. N plus 1 and n plus 1 gets cancelled out. So what are we left with? We are left with this limit n tends to infinity. We are left with this n upon n plus 1 whole to the power n. In the numerator, we are left with this n to the power n, and the denominator we have n plus 1 whole to the power n. Okay. So now this is easy limit to simplify. We all know how do we simplify this. We can write this as limit n tends to infinity. This is basically n to the power n upon n plus 1 whole to the power n. So this is actually, we can write this and simplify as limit n tends to infinity 1 upon 1 plus 1 upon n whole to the power n. The same limit, which is, how much is this? So limit as n tends to infinity, this tends to 0. So this is actually 1 upon e over here. Okay, so that is basically what we are getting is limit n tends to infinity an plus 1 by n is actually 1 by e over here. Okay, and we all know by the Cauchy's second theorem on limits, this limit n tends to infinity an plus 1 upon an is the same as limit n tends to infinity an to the power 1 by n, which is our given limit actually. This is our limit n tends to infinity an to the power 1 by n. So if this is 1 by e, so by the Cauchy's second theorem of limits, so basically this is also 1 by e. Clear? So you can match with the answers also. Previously also we have got 1 by e. Over here also we are getting 1 by e by the both the ways. Let's see some more questions. Okay, here we have a nice question. We have to evaluate this limit n tends to infinity n square upon n square plus 1 square whole to the power 3 by 2. And so on. This goes up to n square upon n square plus n minus 1 whole square whole to the power 3 by 2. Now numerator is very simple. We have n square in the numerator. But denominator, we have to adjust this a bit. Here we have n square plus 1 square. Next is n square plus 3 square. Okay, all odd terms are there, which means the next term will be n square plus 5 square. But this is going up to n square plus n minus 1 whole square. Okay. So what I do first, over here we have limit n tends to infinity. To write this in terms of sigma, this is our first target, right? So we write this in terms of sigma. So sigma, we have n square. We'll see the limits first. Later, basically we have n square upon, numerator is n square. So we have n square plus, this is 1 square, 3 square, 5 square. So definitely we shall have 2r minus 1 whole square. isn't it? 2r minus 1 whole square, 4 to the power 3 by 2. Now, limits, this is dependent on the limits. This is not going up to n. R is not going from r is equals to 1 to n. You put r is equals to 1. This will become 2 into 1 minus 1. That's 1 square. This is 1. N square plus 1 square. You put r is equals to 2. This will become 4 minus 1. 3 square. This is 3 square. That is fine. But you put r is equals to n over here. This will become 2n minus 1 whole square. But over here we are having n minus 1 whole square. Not 2n minus 1. We are having n minus 1 whole square. R will definitely start from 1. R is 1. But the end limit has to be not n. Isn't it? This is actually not n. This is going up to n minus 1. So over here we should have n minus 1. So definitely this has to be n by 2. If this is n by 2, then you can figure out if this goes up to n by 2, suppose. If this goes up to n by 2, so you put r is equals to n by 2 over here, 2 cancel out, so n minus 1 whole square will be remaining. Clear? So basically what we have is we have limit n tends to infinity over here. Sigma goes from r is equals to 1 to n. We try to bring r by n format over here. What I do is we try to bring r by n format over here, and by taking out 1 by n also outside. Okay. So here I can clearly see we have r is equals to 1 to n by 2. Here we have n square over here. So we have n square. Okay. I take out n square common from here. So what I get from here, we have n square common. So n square whole to the power 3 by 2. Okay, so n cube will actually come out, isn't it? N cube will come out. So over here we have 1 plus 2r minus 1. This was n square. So we have n square upon 2r minus 1 upon n whole square, whole to the power 3 by 2. So now this gets cancelled. So one of the powers gets cancelled. 1 by n already comes out. So we have limit n tends to infinity 1 by n summation r is equals to 1 to n by 2. Okay. And this is actually basically now 1 upon n times 1 upon 1 plus. This is actually now 2r by n, right? 2r by n. 2r by n and minus 1 by n the whole square, whole to the power 3 by 2. Clear? Now as limit n tends to infinity, this 1 by n will tend to 0. This r by n will turn out to be function of x. Replace r by n by x, isn't it? And as n tends to infinity, this will tend to 0. So we have this integration, the function. Let's write down the function and then we'll see the limits over here. This is actually from 1 upon 1 plus, this will become 2x, isn't it? 2x whole square. That's 4x square. This will turn out to be 4x square. Okay. As n tends to infinity, this tends to 0. So we have 2r by n, replace r by n by x. So we have 2x whole square. So that's 4x square. And over here, whole to the power 3 by 2 dx. Now what are the limits? It goes from r is equals to 1 to n by 2. So definitely this will go from 0 to half over here, 0 to half. You can verify by the same process, taking the lower limit will be what? You divide by n and take limit n tends to infinity. This will give 0 over here. And similarly, in the upper limit of this sigma, it is n by 2. For the upper limit of this integral, what you do is you divide n by 2 and then you divide this n by 2 by n and take limits. So limit n tends to infinity. So this will turn out to be n cancel out. So we have limit n tends to infinity. That means this is tending to. So that's half only. So that's basically you will get half over here. So we have integration 0 to half 1 upon 1 plus 4x square whole to the power 3 by 2 dx. Clear? Now we are asked to solve this integration. How do we solve this integration? We have 1 plus 4x square. What we can do is we can take out this 4. 4 is basically nothing but 4 is actually 2 square. So we have 2 and 2 cube. So 2 cube will come out. 8 will come out actually. So this is basically I'll do it over here. So this is integration. You take out 8 common, 1 by 8. Okay. This is 0 to half dx upon what I get from here, half square half square plus x square whole to the power 3 by 2. Now I put x is equals to tan theta and then solve. You put x is equals to tan theta. In fact, you put x is equals to half tan theta because here we have half. So you put x is equals to half tan theta. If you put x is equals to half tan theta, this will become dx is half sec square theta d theta. Okay. So what this will be? This is 1 by 8 times integration 0 to. You put x is equals to 0, this will still remain to be 0. Lower limit will be 0. You put x is equals to half over here, so this will half cancel out. Tan theta is equals to 1. Theta is pi by 4. 0 to pi by 4 is the new limits. Dx is half sec square theta d theta. So this is half sec square theta d theta. Okay. And then we have the function. We have half square plus this is x square. X square is half tan theta square. Now we simplify this. So this is 1 by 8 times integration 0 to pi by 4. Over here we have half sec square theta. Over here you will get half square, right? In the numerator we have sec square theta. And you take out 1 plus tan square theta whole to the power 3 by 2 was also there. Sorry, I forgot to take this whole to the power 3 by 2. Okay, you take out half square theta you take out, half square you take out. Okay, half square, and this is basically half cube will come out because power was 3 by 2, so half cube will come out. Half cube times this will turn out to be 1 plus tan square theta, that is basically sec square theta, and here we have cube over here, so this whole to the power 3 by 2 is there, so this will turn out to be sec cube theta, isn't it? This will turn out to be sec cube theta, and we have d theta. So here you can figure out one of the sec square theta, and this is one of the sec square theta will cancel out from here. 1 by half cube, that is basically 1 by 8. Okay, 1 by 8 over here, and definitely here what I can get in. So basically here also 1 half was also there. Outside also we had 1 half over here. This half was also there. So you can write this to be 1 upon 16. Okay. So this 1 by 8 and this is 1 by 16. So that's 8 by 16. That is basically 1 by 2. So we have integration 0 to pi by 4. Here we have 1 by sec theta. 1 by sec theta means we have cos theta d theta. Clear? Now simply integrate this. So we have half times integration of cos theta, that is sin theta. Range goes from 0 to pi by 4. So this is half times sin pi by 4, that's 1 by root 2. So this is basically 1 upon 2 root 2. I hope calculations are clear to you. Okay. You will try out the calculations on your own. Do not, if you are seeing the video, then simply pause the video and simply try out the integration calculation on your own. Okay, next we have this question from JEE Advanced 2013. We have limit n tends to infinity, 1 to the power a plus 2 to the power a and so on up to n to the power a upon n plus 1 whole to the power a minus 1, and this sum is given. This is equals to 160 is given. We have to find the values of a actually. Okay. What are the values of a? Possible set of values of a. What I do over here, what I can observe from here. First of all, we have limit n tends to infinity. 1 to the power a plus 2 to the power a and so on up to n to the power a. So I can write this in terms of summation. Summation r is equals to 1 to n r to the power a. Okay. Then denominator we have n plus 1 whole to the power a minus 1. And this sum we have na plus 1, na plus 2 and so on, na plus n. So we can write this in terms of sigma r is equals to 1 to n. This is na plus r. Okay. Now what I do? I try to bring this in the form of f of r by n. That's standard limit format. What I try to bring is, I try to what I do is I divide by n over here, divide the numerator and denominator by n. Okay, so this is 1 by n and this turns out to be 1 by n. Now I try to bring r by n format over here, isn't it? I try to bring r by n format over here. To bring r by n, what I do, I divide the numerator and denominator by n to the power a. Clear? So if you divide the numerator and denominator by n to the power a, this will become r by n to the power a. You're dividing by n to the power a just to bring this r by n format over here. Here we have n to the power a. Okay, dividing by n to the power a, and over here in the denominator also you are dividing by n to the power a. So what happens over here? What do? You divide this by, you separate that n to the power a, write it as n to the power a minus 1 into n to the power 1 over there, right? What I'm trying to say is, you try to write this n to the power a as n to the power a minus 1 into n to the power a. Sorry, into n to the power 1. Okay. Divide this by n to the power a minus 1 and divide this by n to the power 1. That is basically n. Clear? So what happens over here? So this turns out to be limit n tends to infinity 1 by n sigma r is equals to 1 to n r by n whole to the power a. Divide this part by n to the power a minus 1. So this will turn out to be 1 plus 1 upon n whole to the power a minus 1. It is getting balanced over here, right? And 1 by n sigma r is equals to 1 to n. You divide by n to the power 1. So this will turn out to be a plus r by n. Now we distribute the limits over here. Limits are distributive. You can distribute the limits in the numerator and denominator. So if you distribute, so numerator will be limit n tends to infinity 1 by n sigma r is equals to 1 to n, and this will become r by n to the power a. Denominator will be, you take limit n tends to infinity, this will tend to 0, right? So we have 1 to the power a minus 1. So this will have 1 only. So 1 times 1 by n, we have limit n tends to infinity 1 by n summation r is equals to 1 to n a plus r by n. This is what we are having. So we are basically simplifying the left hand side and we have to equate this to 1 upon 16. Now this is simple. We have 1 by n over here. Summation of this format is given. So we can directly replace this by integration. So what is the numerator? Numerator is integration 0 to 1 limits from r to n 1 to n. So we have integration 0 to 1 x to the power a dx r by n by x, and denominator we have integration 0 to 1 a plus x dx. Now we simplify this. So we have x to the power a plus 1 upon a plus 1, right? Range goes from 0 to 1 upon, we have integration of a plus x, that is basically ax plus x square upon 2. Range goes from 0 to 1. And this is equals to 1 upon 60. We are going to equate this and find the possible values of a actually. So you simplify this over here. So you put a 1 over here. So we have 1 upon a plus 1 and 0 for this is 0. So this is 1 upon a plus 1 numerator upon what I have get from here. We have a plus half from here, right? I get a plus half over here. And this is equals to 1 upon 60. So you simplify this, you will get one quadratic relation from here. We have a plus 1 into 2a plus 1. This will be equals to 120. And if you simplify this, you'll get the possible values of, a from here is 7 and minus 17 by 2. You can verify with the options. We have the option verifications. You'll get the answer to be 7 and minus 17.